One of them will be talked about tomorrow by Giulio Salvatore, sort of all-loop non-planar generalization of amplitude-ionic ideas for trace phi cube theory. As you'll see in his talk tomorrow, there is some sense in which gravity, something like gravity, is forced on you by this construction, by these ideas. I will talk about some work with Johannes and Jera on loops of loops and a way of heading towards extracting non-perturbative information from positive geometries, and you'll see why I use the word negative geometries in a moment. Now, I've seen how much Giulio has been suffering to get an insane amount of material in a 20+5-minute talk, so I decided I will try not to be an asshole for once and actually try to end with the same amount of time as everyone else, so we'll see how I do. Now, you all know this basic connection between gravity and Yang-Mills goes back to first perturbative string theory, and they're really associated with this cartoon of two open strings being able to fuse and turning into a closed string. And again, this is already seen in perturbation theory as KLT, and it's more modern avatar of color kinematics duality in BCJ. That moved on first to a qualitative picture of how open and closed strings were related to each other. If you imagine closed strings hovering in the neighborhood of a black hole horizon, where you'd only see half of them from the outside. So what looks like from the outside, a closed string from the outside can look like an open string stuck to the horizon. And that very vague idea actually is quantitatively correct in the context of the ADS-CFT correspondence, where you imagine throwing a closed string down an empty de Sitter throat, and the sort of dynamics of the open strings of the brain that created that throat infinitely far away is dual to the theory of closed strings in the bulk. Most of the talks in this meeting are on this side, on the perturbative side of the connection between gravity and Yang-Mills. Today, I want to talk about something that's broadly motivated from the other side. And of course, we'd like to understand the best understood example of ADS-CFT, even for n=4 super Yang-Mills. How is it that you begin with a theory of gluons at weak coupling, at weak Atoph coupling, crank up the Atoph coupling and have something gravitational emerge, something like empty de Sitter space emerge at strong Atoph coupling? And of course, this is a problem that's been explored from many points of view for many years, especially for n=4 super Yang-Mills. Integrability in many cases gives us a very powerful method to try to understand, in some sense, the emergence, at least solve the theory of strong coupling and then see what happens for various observables as you try to match that with the calculations in the ADS. But at least from my own point of view, there's a lot of heavy machinery involved in this approach, integrability, the massive amount of difficult mathematical physics. And for such a basic general phenomenon that's supposed to be very, very general, one would ultimately like, I think, a simpler picture for how it happens. So that's our motivation here, is we want to begin, at least take a different line of attack on this question. How do we go from gluons at weak coupling to empty de Sitter space at strong coupling? Or how can we solve the theory at strong coupling using ideas from amplitudes? And of course, there's a very old fantasy. Can't we just sum all the diagrams? And, going back to the 70s and the picture of the diagrams getting denser and denser and turning Feynman diagrams into worldsheets, there's this idea that you might see the emergence of strings as you go to strong coupling, but you have to be able to sum all the diagrams. And an inspirational toy example, many of you know better than I do, is just summing ladders. Okay, and so here's a simple example where we start with a box diagram, but there's actually an infinite series of these diagrams. Of course, in principle, we have to sum all the diagrams, but imagine just focusing on one set for a moment. Here we know there's a very beautiful method for actually summing all of these diagrams. And it goes under this boxing trick. The basic point is that if you imagine this as a function of x1, x2, x3, x4, the sort of dual variables, if you take the box with respect to x1, that collapses this propagator and you just go down to just 1. So the box operator acting on this box gives you 1. And in general, the box operator acting on an L rung ladder is an L-1 rung ladder. And therefore, if you make a generating function that sums all of these ladder diagrams like so, it's going to satisfy a differential equation, a linear differential equation. And these things, these functions only depend on two cross ratios, two conformal cross ratios. So the box actually just turns into some second order operator in Z and Z bar. So there's some del ZZ bar plus G squared F equals 0. Okay, so you begin with a perturbative picture, but from it you extract this differential equation, which is itself non-perturbative. In principle, this equation does not have to be solved with small g. You can imagine solving it. You can imagine taking it to strong coupling, the exact solution that you find. You can imagine doing a perturbative expansion at large G. There are many things that you could do with this equation. So even though you got it from this perturbative starting point, the equation itself is non-perturbative, and then you can try to understand something about this structure. Now, what's missing in this picture is obviously a second direction. Okay, so if you want to imagine summing all the diagrams, well, we have more than ladders, and in fact, we have to sum diagrams are about as big as they are in both directions. They're not just skinny in one direction. And it's a little difficult to imagine what kind of differential equation is going to capture all of this, simply because there's very few invariants. On the outside, I just have Z and Z bar. And so somehow you have to get another direction in town if you want to pursue this kind of strategy. So at least that's a zeroth order problem with this kind of strategy. How are we going to see this other direction, something that isn't just long and skinny, a ladder? All right, now, of course, over the past decade, there have been some developments in new definitions of thinking about what amplitudes are associated with positive geometries and amplituhedra. And we're going to talk about that. We're going to begin with that starting point and then think of another way of organizing the expansion for the amplitude that's going to allow us to think about the problem in a new way. That's what I want to tell you about today. But let me first tell you what observable we're talking about, because I think this is sort of interesting all by itself if you care about n equals 4 super Yang-Mills. I think this is the simplest finite observable that we can talk about. You know, what quantities people talk about n equals 4? They talk about the cusp anomalous dimension. Well, okay, that's a number which depends a function of g. And then after that, we jump to things like the remainder function, which are quite complicated polylogarithmic functions, even in the simplest cases of many variables and so on. So we go from 4-point scattering, which contains a cusp anomalous dimension, and we jump to 6-point scattering, something a lot more complicated. Well, there is something in between, which is extremely simple and is a function of a single variable. And what it is, as usual, to cancel infrared divergences is a ratio of quantities. So you might imagine that we're calculating the expectation value of the Wilson loop with a Lagrangian insertion divided by the expectation value of the Wilson loop itself, which is something finite. All the IR divergences cancel in that quantity. All the cusp divergences in the Wilson loop picture cancel in that quantity. And it also has a very practical interpretation. Imagine you took the log of the amplitude. We know the log of the amplitude is only log squared divergent. So there's something special about taking the log that at L loops takes the log to the 2L divergence and gives us just something that's log squared divergent. But what that means is that if you imagine taking the L loop integrand and integrating over all the loop variables but one, if you leave one of them free, the resulting function will actually be completely finite, totally finite function of that last loop integration point. And there's a single cross ratio that you can make involving that last point and the 5 variables and the 4 variables for n equals 4-point scattering. And that single cross ratio is Z. So this is a function of a single kinematic variable Z and a function of the Topf coupling. Okay, so, and of course, it's 4-point scattering, so it's basically guaranteed to be some interesting, weak coupling has an interesting polylogarithmic expansion as a function of this polylogs in Z, and of course, as a function of the Topf coupling. So this is the object that we want to talk about. And what approach are we going to take to trying to understand it? Well, we're going to think about the definition of what the amplitude is, the 4-point amplitude is given by the amplituhedron. This is a quick summary of what the definition is, a complete summary of what the definition is. For the L loop integrand, again, in dual variables, we imagine we have the points 1, 2, 3, 4, and then we have L points in the dual spacetime corresponding to the loop integrations. In twistor space, in momentum twistor space, we think of these as 4 points, Z1, Z2, Z3, Z4, giving us this polygon on the right that gives us the null separated points on the left. And each one of the loop variables is just some line in twistor space. So we conventionally call them, we label the lines by 2 points on it. So we call it AB1, AB2, and so on up to ABL. So that's our data. Now in this space, there's a certain interesting positive region, which is defined by the amplituhedron. And it's defined by asking that every one of these lines has a certain positive relationship to the external points. If you've never seen these brackets, this is really just saying back in space-time language that the distance squared between any one of these points, any one of the loop points, and the external data is positive. Okay, so there's some external positivity. Each one of these loops has to have some external positivity relative to 1, 2, 3, 4. And notice this external positivity depends on the cyclic ordering of the 4 external points. Okay, so there's some ordering in this definition of positivity. But the juiciest part is something different, a rather different kind of positivity. We just call it mutual positivity between the different loops. So each one of the points, each one of the pairs, yi and yj, yi minus yj squared has all got to be positive. Or in the language of momentum twistor variables, AB alpha, AB beta have all got to be positive. Now, this is a quite different thing. You see, something with the cyclic external ordering smells like Yang-Mills. Something here with mutual positivity is rather different. It's like each loop line is its own object, and they're interacting with each other in some way that's totally permutation invariant. Okay, and I'm going to denote this requirement that all the AB alpha, AB beta are positive for a given loop order. I'm just going to draw a dot corresponding to every loop line, and I'm going to connect any pair of dots with a wiggly line if I demand that AB alpha, AB beta is positive. So here it's pretty boring. The graph is pretty boring. It's just a complete graph because all pairs are forced to be positive. Okay, so that's it. That's a one-line definition of what the amplituhedron is. And we're supposed to do the integrand at L loops is supposed to be the canonical form with logarithmic singularities on and only on the boundaries of this space. Okay, so we're going to begin with this definition and then try to say something about the simplest observable that we just talked about, also at finite values of G. All right, so what are we going to do in this talk? So I have 2 things that I want to do in the rest of the talk. First, I want to tell you why, just starting from the amplituhedron, it's very natural to discover the log of the amplitude. In other words, we normally think that we take the log of the amplitude because we know a lot about physics and infrared divergences and the exponentiation of IR divergences and so on. I want to explain why purely from the almost just the combinatorics of the definition of the amplituhedron, it's very natural to think about the logarithm. And in fact, there's a beautiful formula that the log of the amplitude, just like we think about the amplitude itself at L loops as being given by all of these mutual positivities, I draw a graph and I draw the complete graph on L loops and I demand that they're all mutually positive. So the logarithm of the amplitude at L loops, and I sum over all L weighted by G squared in order to get the amplitude itself, or if you like the integrand itself, which I integrate to get the amplitude. The logarithm is the sum over all connected graphs, so not complete graphs, but connected graphs on L nodes. But now I've changed from wiggly to solid lines. And every one of these graphs now means that any pair of nodes that are connected, instead of forcing AB alpha, AB beta to be positive, as in this previous picture, I actually demand that they're all negative. And so that's where the word negative in our negative geometry comes from. All of the external guys are still forced to be positive, but all the mutual guys here in these new graphs are forced to be negative. So we go from having a single graph to the sum over all of these connected graphs. Now, what's remarkable is that every one of these terms by itself, every one of these things defines its own geometry, every one has its own canonical form or integrand, and if you integrate every one of them individually, you get something completely finite as a function of z. Okay, so this answers a question that many of our mathematician friends have been asking us positive geometers for many years. Please give us some positive geometry that we integrate to get a finite polylogarithmic expression, just so we can start thinking and working on it. And we could never give them one before. You know, they're all complicated. We could, but involve ratio functions or more complicated things. Here it's a super clean, beautiful thing. There's a well-defined positive negative geometry, if you like, associated with all these negativities, and each one of them by itself gives you a finite polylogarithmic object at L loops. Okay, so that's statement number one. So this first statement is essentially trivially combinatorial, as I'll explain in a second. The second is that this expansion, the second comment is that this expansion, each one of these pieces is finite by itself, but each piece has no Feynman diagram interpretation, planar Feynman diagram interpretation at all. It's not like PCFW where they have spurious poles and stuff like that. Everything is perfectly local, decent poles, but they cannot be thought of as combinations of planar diagrams, products, anything. They don't have a natural diagrammatic. Interpretation. They have a natural dual diagrammatic interpretation, but they don't have a natural diagrammatic interpretation. And you see, it's a little funny that now it looks like we're drawing diagrams, graphs, weighting them. So it kind of looks like we're talking about another kind of theory now in loop space. And so what we're going to do is make a distinction between these graphs that don't have loops and have loops in them. Okay, so we're gonna deform the amplitude by a loop counting parameter. Remember, this is no longer loops, the ordinary loops. This is loops in this funny space of mutual negativity. So what we're going to do is deform the amplitude by a new parameter y, and that means that we're going to sum over all these graphs. But any graph that has L loops in it, we're going to weight by some new factor y to the power of little l. Okay, so when y is equal to 1, we go back to the usual amplitude. But we're going to think about this as a function of y. It's sort of motivated by the idea that there's some kind of theory in this loop space. And what we're going to do is first try to understand this theory at tree level, quote unquote tree level, which means small y, which means we're going to sum over all of these trees. Okay. We're going to sum over all of these trees, but it will be non-perturbative in the actual Yang-Mills coupling constant. Okay, so we're not solving the whole problem, but we're deforming the amplitude in a way that's natural from this geometric perspective, and we're going to solve the classical part of the problem, but non-perturbatively in G. As you'll see, this is kind of like a one-step generalization of the idea of summing over boxes, except with a number of new ingredients that we're going to see in a moment. All right, so let's just go through the 2 points I wanted to make. First, why would we discover the log of the amplitude, and why is it related to negative geometry? And it's an utterly trivial point, but still quite cool. Remember, I told you the amplitude at L loops is this complete graph. Okay? Those are the positivity conditions that I have to impose. Everyone is positive with everyone. But note that asking for everyone to be positive, for a pair of guys to be positive with respect to each other, and a pair of guys to be negative with respect to each other, the sum of those two regions is just imposing no constraints between the two of them at all. So in other words, if I'm given an AB1 and an AB2, there's a region where AB1, AB2 is positive, there's a region where it's negative, and if I take the union of those regions, I'm not putting any constraints between AB1 and AB2 at all. So that means that I can replace every one of these wiggly lines by two disconnected dots minus a solid line. And that converts this expression from a single graph to a sum over all graphs. And you see, all I'm doing is going through the whole graph and deleting some edges and converting the other guys to solid lines. And because there's a plus sign here, when I move it to the other side, there's a minus sign, there's a factor of -1 to the power of the number of edges in the graph. Okay, so this is a totally trivial thing. We begin with one graph, and we see that it's actually the sum over one graph with positivities is the same as the sum over all graphs with this weighted minus sign of the negativities imposed. And now comes the second point that we know goes back in combinatorics to the early 1900s, and we all learned in some early point in quantum field theory. The relation between generating functions for all graphs and connected graphs is just given by exponentiation. Okay, so if I take the logarithm of m, therefore, it's the sum over all connected graphs of this sort. Okay, so that's what I claimed before. Now, once again, each one of these graphs has no Feynman diagram interpretation, but each one by itself, if you were to integrate it, would just give you something that's log squared divergent. Okay? And now I'll explain why that is in a moment. But let me move on from this and just do one more small combinatorial point, where we're ultimately interested in not the log of the amplitude itself, but what we get when we integrate over all of the loop variables but one. So now I want to tell you how to think about the integrand that you get if you fix one of these points. We're going to fix one of these points, and the previous graphical rule about the log turns into this rule. Okay, so the point that I'm fixing, I'm just going to represent by this x. And here's what I get. I get x, and each one of these black dots is one of the unfixed variables that I'm going to integrate over. And again, each line is telling you that I'm imposing a mutual negativity. Okay, and so you really have a graphical expansion. So this is all I have in the if you like, this would be the log of the amplitude at two loops where you're fixing one of the loops. So it only depends on one free loop variable. This would be the log of the variable of the amplitude at three loops where you fix one of them. And so you see some of the diagrams are trees, some have loops. And I forgot, actually, the whole point of writing this was some important symmetry factors, 1 over 2 factorial in front of these diagrams, 1 over 3 factorial in front of these diagrams, and so on. Okay, so, but that's it. You just draw all possible diagrams beginning with this X, and they go out any way you want with trees and loops and anything you like. And again, the claim is that every single one of these things gives you something finite when you do the loop integral. So for example, this first guy is pi squared plus log squared z. This interesting guy, now coming at 3 loops or 2 integrations, is a weight 4 object. Again, so it's some harmonic polylog in z and lots of log logs and corrections and some finite pieces, but they're all totally finite. And we can, in these low loop cases, we know the integrands, we can use standard methods to get the answers. So each piece by itself is a finite polylogarithmic object. Now, why are these things finite? The reason is that there's a very simple sort of deep connection between the positivity and negativity properties and the presence and absence of soft collinear divergences. Where do divergences come from in these loop integrals? They come when the loop momenta go into the soft collinear region. Now, in the momentum twister language, the soft collinear region is extremely simple to describe. It's when when the loop variable that corresponds to a line in momentum twister space AB, when it passes through the point 1 while lying in the plane 4, 1, 2. So that means that I can parameterize it by saying that A passes through 1, but B is somewhere in here, so I can write it as 4 plus some number x times 2. Now, in trying to see what possible, whether we actually have a residue, whether the integrand has support in the soft collinear region, we want to see whether this region is actually allowed by the amplitude-hedronic geometry. And if you demand the external positivities, as I mentioned before, that forces this variable x to be positive. But if you demand the internal positivities, it demands it to be negative. So, in other words, if the loops are mutually negative, that forces x to be negative, and so this region does not exist. So this negative amplitude-hedronic region kills all of the soft collinear singular points. In fact, the only singularity you get is if you take all the loop momenta into the collinear region together. That's why you get only a single log squared divergence if you integrate it over everything. But if you keep doing the loop momenta free, you get no divergences at all. So you get something totally finite, and that explains the finiteness that we see. All right, so that's the object. Each piece has no diagrammatic interpretation. Each piece is finite by itself. If we add them all up, we get we get this integrand for the log of the amplitude, or this Wilson line with the extra point insertion. And now what I want to do is look at a subset of these diagrams and solve them. Okay, so I want to sum over all of these tree diagrams. So again, we're imagining that we've deformed the theory by adding this parameter y, and I'm going to work at y tiny. So I'm interested in summing all the trees in this sort of funny theory in loop space, but at all values of the coupling constant g. Okay. Okay, so to begin with, let me define a generating function for all the trees just graphically like this. So it's a sum over all graphs with one insertion like that. It's also useful to define something closely related, all graphs that begin with the x going up to 1 point and then going to all the trees after that. Okay, so those are two closely related sets of graphs. Now, very importantly, there's a simple relationship between these two sets of generating functions, which is that getting all the graphs is just the exponential of getting all the graphs where you start off and you go to one spot. And this is really just saying that you start and you go somewhere, and all possible ways of going are given by this exponential. This is another. It's not the same relationship that we're used to between connected and disconnected graphs, but it's another sort of very basic combinatorial fact about summing all possible trees. Okay, so this generating function and this generating function are simply related in this exponential way to each other. Okay, and you'll see why that's relevant in a second. Now, let's take any one of these graphs that are trees, like this one is the simplest one. Okay, so remember, all I'm saying here is that I'm finding a form in the space of this variable x1 or the corresponding line AB1, but I'm just demanding a mutual negativity between 1 and x0. Similarly for all the rest of these guys. And now here's a crucial point, because in all these examples, x0, the only guy that it talks to is one person that then talks to everyone else. We know ahead of time that when we integrate this, the boxing trick works again. Even though they're not standard Feynman diagrams, the boxing trick works again. And if I take a box with respect to x0, I just collapse this. Okay, I just collapse on whoever x0 connects to. So box with respect to x0 gives me this thing as x1. Box with respect to x0 in this example again just collapses x0 down to whoever it attaches to. And therefore, box of the whole generating function is just equal to negative g squared. The box of this generating function where you go out and connect to one guy is just negative g squared, the sum over all trees, as we see in this, in these examples. Okay, so the boxing rule gives us this interesting relationship. Now remember that we already saw that that these two things are related by an exponential. This guy is the exponential of that guy. And therefore, if I call h the log of f, which we did before, I get box h plus g squared e to the h equals 0. The second point is that just like in the usual boxing case, the actual box diagram depends only on two conformal cross ratios, z and z bar. In the present setting, it only depends on one variable, z. And so the box operator is just this trivial thing, dd log z, z dd z squared h3 plus g squared e to the h equals 0. So we've discovered that summing over all the trees is captured by this interesting nonlinear differential equation. Of course, this is closely related to very famous differential equations like the Liouville equation. I don't have time to explain, but there's a very simple boundary condition that tells you that h at z equals -1 has to equal 0, and also that h has to be an even function of log z. So we know those two extra facts. But what I want to stress here is that this is the kind of analog of summing over boxes, except when we sum over boxes, we get a linear equation. We don't get a hint of this other direction, whereas here we get a nonlinear equation. And here we get this nonlinear equation because we're also not just summing something that looks like a chain, but of course it doesn't have a diagrammatic interpretation, but in this negative geometry world, we're summing over these growing trees. And the sum of over those growing trees turns this into a nonlinear equation rather than a linear one. But in any case, it's trivial to solve this equation with the boundary conditions, and here it is. This is what we get. It has this very simple form. Just looks like a is a constant. Looks like a squared over g squared, z to the a over z to the a plus 1 squared, where a is fixed by the boundary conditions by this simple formula: a over 2g cos pi over 2 equals 1. Okay. So, for example, at weak coupling, here I'm plotting the function a over 2g cos pi over 2. At weak coupling, this equals 1 forces a to be close to 2g. But at strong coupling, as g gets enormous, a is just forced to go close to 1. Okay, so we can and we can actually just expand what this looks like both at weak coupling and at strong coupling. So at weak coupling, this is the expansion. There's the first term that I showed you before, it goes like log squared z plus pi squared. But at strong coupling, it also has a nice expansion in powers of 1 over g squared. And what's really cool is that it begins with a rational term. Okay, so it really looks like this classical theory that we've summed in loop space. When we also go to very strong coupling, it begins with something that looks rational, and then there's a series expansion in powers of 1 over g squared that are given by transcendental corrections, just simple logarithmic corrections in this case, but nonetheless. Okay. So we start getting some hint of being able to extrapolate from arbitrarily weak to arbitrarily strong coupling. I'll just say quickly that once you have this function, if you wanted to get a gamma cusp out of it, you can. You just have to do the last integral, and there's a simple way of doing the last integral and extracting the log squared divergence from it to get the gamma cusp. And again, if we knew what this whole function was for y equals 1, if we summed over all the graphs, this would be the cusp anomalous dimension. But we're doing it now for the trees. This funny deform theory where I've just summed over all of these trees. But from there, we get an interesting formula for the contribution from these trees to the cusp anomalous dimension. So some gamma tree of G, which turns into this beautifully simple thing, where again, A is fixed in exactly the way that I was telling you before. Once again, you can expand gamma at weak G, where we get just a power series in G squared, and at strong G, where you get a power series in 1 over G, not 1 over G squared, 1 over G. So anyone who's looked at perturbation theory in anti-de Sitter space knows that's one of the magical things that happens, is that in ADS, the strong coupling and expansion in 1 over the square root of the Tooth coupling and not the 1 over the Tooth coupling. That's exactly what we see here. And we get an expansion of gamma cusp in powers of 1 over the square root of the Tooth coupling, not the Tooth coupling itself. Okay, so that's it. Let me just summarize. We now have a direct connection between positive geometries and finite, in fact, polylogarithmic in recoupling expansion amplitudes. We're sort of proposing the study of a deformation of the amplitudes. That's not obvious from the normal Feynman diagram space-time point of view, space-time process point of view, but is natural from the point of view of these positive geometries, where we sum over all of these graphs, weighting these loops in loop space by some expansion parameter. We have determined what this classical limit of this theory is this new parameter y goes to 0. We're interested in knowing what it is as y goes to 1 to get the real amplitude. And all of this, the most obvious immediate thing to do is move beyond this boxing trick. So you see, nowhere here did I even have to work hard to tell you what the integrand was or anything, because we could just tell that there's a simple differential equation that related the geometries to each other directly. I didn't have to do any work. I took the box on the external thing and I saw that it took me from one geometric region to another geometric region. But the most obvious thing we need to understand are really the amplitudes or the integrals associated with these loops, really loops in loop space. Now we know what the answers are for these expressions at low orders in perturbation theory, at 2 and 3 loops, 2 and 3 integration variables. And there's some interesting pattern in them. I mentioned that everything is just a function of z. The polylogarithmic symbol is a function of only 2 letters. There are exactly 2 letters, and one of them shows up in the, one of them shows up in this tree problem, and the other one begins to show up when you have loops. And so we don't have enough data at 2 and 3 loops to really be able to say something more conclusive than that. But it certainly looks like as you start including loops in this negative geometry space, you start having access to this other variable in the symbol in some interesting way. And a very rough hope is that there's some kind of operator that acts on the function associated with the graph G, and it somehow is related to simpler graphs, gives us sums over the other graphs to some coefficient CG prime with FG prime. Now that's literally what we saw in the case of these trees. The hope is that something like that happens more generally. And again, this is all along the lines of this other direction we were talking about. Kinematic variables on the outside, and you can't imagine much more than something like an operator box that depends on one variable. We need extra directions to see all the extra possible complexity in the diagrams, and we have at least another set of large numbers of objects, not just one. We have this whole set of graphs, and one can hope that that this kind of recursive structure, which we've already seen in these trees, would actually hold in some more general setting. And so I think so this is all just steps in the direction of this general program. So we'd like to understand how to go from positive geometries to amplitudes, but not just doing the integrals. We really hope that there's some kind of non-perturbative definition for what amplitudes are that is the analog for amplitudes of what the amplituhedron is for integrands. We'd like to see how antidecision space emerges from the amplituhedron. It should. We know everything in principle about the one-line definition or half a page definition for the amplituhedron for all n and k and l. Somehow it's strong coupling. We have to be able to see this physics emerge. And I've thought for a long time, the sort of slogan that I've said, that it's likely that the amplituhedron is about the integrand and is about the integrand for gluons. But purely from the positive geometric point of view, we believe that there's some kind of dual of the amplituhedron lurking out there that we've still not found. And my strong feeling is that it both exists, and its existence is about strings and ADS. Okay, so I've said nothing about this fantasy in this talk, but I think the very preliminary steps we're taking are heading in this general direction. Okay, thanks a lot.
Thanks a lot, Nima. So Lance has a question.
Hey, Nima, fantastic talk. Especially love you got rid of those integrands. It's great.
Yeah.
Question about the radius of convergence of the perturbative expansion of the y goes to 0 limit, because when we do ladders,
yeah, we should check it. I have not checked. You want to know how much smaller it is than 8, right?
Yeah, I predict that it's a factor of 16 off in G squared from the cusp anomalous dimension. Because when we summed the double pentagon ladders, we found that mismatch. And basically ladder, you're not doing exactly ladders, obviously, but it looks a little bit ladder-like. So I was wondering if it's also has too slow a growth rate to be important at strong coupling.
For sure. In fact, and actually there's let me say a couple. So yeah, we should check. We can almost check in real time, but anyway, we'll definitely check before we write the paper what the radius of convergence is. I want to say that it's kind of ladder-like, but it's a little more because it goes in, ladders, as I said, ladders just go one way.
No, sort of I agree. More. It's not exactly.
Yeah, right, but I totally agree that it should not. So actually, I would hope that it's actually that it's a little better than ladders, but still far away from.
It'd be nice to know what that number is, how big it is.
Yeah. I think that maybe the most encouraging thing to me is that when we go to this strong coupling, we get something simple. We get these rational functions at the other end, and that we get this 1 over square root Topf coupling expansion. That's one of the weirdest things. Where the hell does this 1 over square root come from? And that's sitting there already. That's sitting there already at even as y goes to a 0. The other thing which is clearly off about this, and which you can see from the strong coupling results, I mentioned that we know a boundary condition which says that when this variable z equals -1, this thing vanishes. And that's very simply, you can see it from the integrand, even if you don't know, with no detail, there's just a factor that forces it to vanish there. And so, for example, that log squared z plus pi squared, I mean, that's what you get because z equals -1, you get 0. However, we know that the strong coupling, we know the strong coupling answer for this quantity from, I think, work of maybe even Radu. I'm not sure. But anyway, we know, I can't remember, but we have the strong coupling result for this quantity, and it definitely does not vanish, and it doesn't come close to vanishing at z equals -1. So clearly, this subset is missing something. I think it would be interesting if our integrability friends maybe turn their attention. It might not be very hard for them. I don't know. It's really significantly easier than the remainder function. I mean, it's a much simpler object, and it would be very cool if they could at least give us the answer. Or if not, if we could see why it was.
Do you have any single logs of z? Do you have any single logs of z? Do you have any single logs of z? Or is it, as you take z to 0, is it dominated by log squared of z, but do you have single logs of z?
Oh, I'm not sure. I mean, these trees are definitely log squared. These trees are just are even in log z.
I just wondered if there's any chance you could see the collinear anomalous dimension, the collinear anomalous dimension underneath the crust.
I don't remember. It probably if maybe Yara or
no, it was just log squares, right?
I think it's just log squared. But even for all the diagrams, right? For all the that's my feeling is it's just log squared as well. But yeah.
Okay, thanks a lot.
Thanks a lot.